So now I think we are online. Um, I'll start by introducing myself. My name is Stefan. I will be the coordinator of this event. Be aware this event will be recorded, and so if you don't want to be on the record, please disconnect now. If you have any questions, please ask them and we'll take them afterwards. And now Les will take it from here and introduce the two speakers today.
Yeah, hello and welcome to this event. We are happy to have the chance to look more into prediction of data. And with us today we have two persons that are very familiar to blue fragments and that we know fairly well. Iben from Convex, so maybe you could introduce yourself, Iben.
Yes, I am a project manager and the lead data scientist at Convex. I have a background from Technical University of Denmark. I've been with the Convex for about 5 years, and my main work there is to develop mathematical models to help increase the focus on increasing the quality of our forecast.
Yeah, and we actually know you because we use your forecast to predict frost, which is used in to get an idea if we need salt on the roads.
Yes, we are driving our own numerical weather prediction models, and we are providing road temperatures, ground surface temperatures for you. Yes.
Yeah, and to the bottom right, at least on my screen, Nicola, who we also know because we have done some collaboration. Nicola, maybe you could introduce yourself.
Yes, so I'm Nicola. Hi everyone, and I work at DHI. I am a water resources expert, and most of my work focuses on forecasting. So create system that can forecast hydrological condition, and among all, flood and drought are the one that we're working mainly with.
Okay, perfect. Yeah, and I think the agenda for now is that you will both get half an hour. We will start out with Iben, and afterwards, when both of you have done the presentation, we will ask questions. So we will try to follow up in the comments along the way, and then ask you a lot of questions hopefully afterwards. So Iben, if you are ready.
Yes. As we are wind power forecasting provider, that makes sense. I'll talk about 3 main topics. First, I'll talk about what we do in Convex. Then I'll talk about how to create a valid prediction model. And then I'll talk about our suggestion or our solution to do predictions on rare events. So in Convex, we are doing a full range of things, but they all focus on some sort of weather, or based on some sort of weather-related issue. So we're doing power forecasting for wind and solar parks. We're doing Med-Ocean services, which is providing forecasts if a client needs to be able to do maintenance in a consecutive, let's say they need to do maintenance on some offshore position for 10 days in a row, and they need the waves to be less than a certain height, we can help them forecast when or help them plan when to do this maintenance task. And then we do all the weather services, and we're providing weather data to a lot of clients, and we are driving our own numerical weather prediction models. If we're talking about weather and power forecasting, we are what we do is that we drive our own numerical weather prediction models, which gives us insight into the future in a grid of what is the wind speed, what is the temperature, what are other meteorological parameters, and then we have typically we have a historic production from a wind farm, and then our task, our product in the power forecasting service, our product is the forecast. So we need to provide them, our clients, an estimate of what is the production of their wind farm tomorrow. So energy is sold and bought like on the stock market, and they need to set in a position every day at 10 o'clock. They need to say what is the energy produced tomorrow, and we are helping them doing that. So I'm talking a lot about forecasting, and this is a prediction event or event on prediction data, prediction of data. I try to define what is the difference, or is there a difference? I'm not a native English speaker, so I might not be correct here, but I'm saying here that a prediction, that's more a statement of some outcome that is the consequence of something. Whereas forecasting is a prediction or an estimation of future events that is based on some available facts. There's and you could say there might also be most likely also a temporal or time component in the forecasting term. Basically, what we do is we have a lot of historic data. We have knowledge of where's the position of the wind farm, what is the historic production, what is the weather pattern in that area. Historically, we have some features, and we feed all of this into our prediction model. We train it, and out comes our forecast, which is the product we send to our client. And then I'm making a bit of a disclaimer here, because I will be talking about how to create a prediction model based on historic events, but that might not always be correct just to base it on the historic events. As we see here, I recently found this statistics on the daily airline passengers in 2019 and 2020 in the US. And this year, something very, you could say, force majeure event happened. So in this case, simply just guessing this year's income, if you're an aircraft company, might not be the best solution for predicting your cost. But that's the disclaimer for that. That is the same issue for the rest of my talk and the methods I'm talking about. So I am, you could say, it has machine learning has become available to anyone. There's easy access, there's free tools. You can use them almost like a black box. You're not supposed to give it instructions. You're supposed to use examples to let it train. And that means that anyone can create a prediction model. You can load a module into Python, and you can type fit, and then you can type predict, and then you've made a prediction model. So my focus here is, and what I would like to address today is, how do you create a valid model? Because we could list a lot of different methods, and there's tons of them, but I think that you should choose the prediction model or method that gives you the best results, but you need to know and be aware of how to evaluate, is it the best results. So basically what we want to do is we want to create a model that represents your data, but it's not memorized. We're not building a parrot that just repeats what we're saying. We want it to be able to represent the future, and the figure in the top here shows our data points in blue, and we want a model that fits the general trends. We do not want a model that overfits and fits all the noise and thereby just memorizes. We want it to be able to represent unseen data. And a way to do that is to split your data so that you are testing and training on separate sets. It's very common to use this cross-validation, where you say you split your data into training and test, and you sort of do different realizations of these training and test sets, and then you say your performance in the end is then the average of the performance over the different folds or the different sets. A key point to remember is that your training and validation and test sets must be independent, and they must be representative for what you want to try, what you want to describe with your model in the future. And for us, we're working with, for power forecasting, we're working with time series, and I guess that's most likely also what you would do in, if you have IoT sensors, they will have some temporal element, I guess. And in that sense, it's very important to consider that for time series, neighboring samples will be highly dependent. So blindly, randomly splitting your training and test sets will give you training and test sets that are dependent, and then you cannot properly evaluate your prediction model. And then in time series, there could also be some seasonality that you might want to represent. I've tried to indicate that in the vertical bars in the lower right. There's 12 bars, each representing a month. So if you try to split your data set by taking a piece of every month and then making your k-fold validation sets by including all months in each fold, that could be an advantage if you want to keep this seasonality. And then you need to consider whether you need to create a time gap between your validation and your test set, your training and the validation set, because you want to make sure that they are independent. And then another thing that is something that we handle and we consider when we are training our models is, do you need to clean your data or do you not need to clean it? I hear that a lot. We need to clean the data because the data is wrong. And I have an example here where we, in the top left corner, we see how, in theory, the relationship between the wind speed and the power is. There's an equation that can calculate this, and this is how it's supposed to be. And then in the bottom right corner, we see actual data. And this is actually, believe it or not, this is actually a very nice data set I've chosen here. They can look even worse than this. And then I'm sometimes met with the fact that my data is wrong. I need to clean it because if I compare it with the red theoretical line, it doesn't fit. I have some horizontal lines. Why do I have that? I have some what we see on the plot is on the x-axis we have the wind speed, and on the y-axis we have the power. And then as I go along and the wind speed increases, the power decreases in the end, and that also doesn't follow the theory. And what I want to, and I would like to quote the chief decision scientist at Google that says, the world you represent by your data is the only world that you can expect to succeed in. So yes, sometimes it can make sense to clean your data, but you need to be aware of what you do. Because if you remove something that is actually a feature that you want to catch in the future, it's maybe not a good idea to clean your data. Okay, so basically, once we've gone through all of this, we've made sure that we do proper training sets. We make sure that we do not necessarily clean the data just because we think it looks bad. We then do a prediction model. And what we do is we do one prediction model for each of the multiple weather prediction models that we have. So we have some in-house that we drive ourselves, and then we have some that we buy from outside. And each of these have different deficiencies or bias, or there's differences in the grid size, and there's all sorts of different things, and they can represent terrain differences in separate ways. So what we do is we train for each available numerical weather prediction model. And for that, we get a power prediction for each of these models. And then we can either send a set of forecasts to our clients, or we can choose to combine the power forecasts from the different based on the different models into a slightly or significantly better overall error reduction. Then I would like to spend the last part of this talk talking about rare events. And when I talk about rare events, I'm not talking about rare events such as the corona events that suddenly significantly reduces the airline passengers. It's not that rare events I'm talking about. I'm talking about rare events that we see in our data, but we still have very, very high class imbalance. And an example of that could be icing. So wind turbines in icy or in cold regions tend to, what can happen is that the ice, the blades are so the ice will be on the blades, and that can either mean that the turbine is less efficient, so that it's still producing a power output, but it's just less efficient. So that if the ice had not been there, the overall power would have been higher. But it could also mean that that the turbine is shut down, or is forced to be shut down because it can be risky to have this turbine spinning with ice flakes on the blades. And the major issue with these class imbalance is that we have two different sets, or we have two different sets, and the majority or the minority class is there's few data sets, and the performance on that class is poor typically because we don't have enough events. And then typically in literature and online, I can see that a lot of people are either doing undersampling or oversampling. So undersampling, that would mean that we would randomly reduce the large class so that both classes are at the same size. But that means in this case that we'll have two very small classes. Another possibility could be to upsample or oversample, I think they call it, the minority class, but that means that we are either repeating data, or I hear that there's also some synthetical approach where you are sort of extrapolating, but we're not really introducing extra knowledge. And then instead what we are doing, we are, so we had clients that would like us to be able to predict these icing events. And we thought, how about instead of having the class imbalance to be a problem for us, maybe we should turn it upside down and say, what if we can exploit the fact that we know that it's rare? So instead, we're trying to utilize these class priors. So we have a prior probability. So for an icing event could maybe be 12% of the data, or the 12% of the historic data we have icing, and the rest we do not have icing. I've tried to indicate on the lower left hand a distribution plot of the temperatures, just to have you could say an idea of what does this mean in this class imbalance. And the blue distribution is when there's icing, and the gray is when there's no icing. And we can see it's not simply just saying when the temperature is below 0, there's icing, because then there'll be a lot of events where there's not icing that we think we have icing. So if we want to utilize these class priors, or this probability that we know, a possibility could be to use a Bayesian approach, where we say we know that the probability of icing, or actually we know that the probability of the temperature changes with the fact that there's icing or not. As we need more than one feature for this, we can see that it's not enough to simply just take the temperature. We need more features. We can expand this to be a Bayesian network, where you have a set of nodes, and each node has a parent distribution, and then each node has, say, in principle, two sets of distributions. One distribution when there is icing, and one when there's not. And then some of these nodes can then have a more than one parent node. And the very small, simple network that I've illustrated in the lower right hand is not the full network for this icing prediction method. It's just a mock-up. It's an example where we see that there are different parameters that are dependent on each other. You could say the temperature is dependent on of the icing. The the temperature distribution is dependent on whether or not there is icing. And you could say visibility is also has different distribution, and it all comes up, or it all ends up with also the season having an influence on how the temperature looks and how the visibility looks. Basically, what we can do then is we can say the end product, the joint probability of whether or not there is an icing event can then be the product of all the conditional probabilities. It requires that we assume that there's an independence between all the features, which there in principle, or which there in practice is not. But it turns out that if we, if we keep that assumption and we say we force the assumption, we can use this method, and in practice it does provide us a product that we can sell, that we can send to, that gives our clients some value. So on this plot here, we see this is one of our products. This is the forecast that we will send to our clients. This is what we see in the dark line, that is, or area, that illustrates the probability of icing that we predict. The light blue line shows the actual power production for this specific wind park in Norway. And the product here is, or the point of this is that you could say, if we send our client from, let's say, on the x-axis here, the numbers here are days. So these are days in December, and it's the latter part of December from a previous year. And then we can say, if we, for instance, from the 21st to the 24th send a forecast to our client with a high production, there can be it can be a risk for them, because if there is icing, the production will not be as high. But alongside this power forecast we can send to them, in these days there's a high production. Along with that, we send them a probability of icing. We say it's a high production of power, and we see that the risk or the probability of icing is low. They can then take this into their considerations when they are trading their energy and they're sending their position into the market. They can be more or less certain on the amount of power that they can insert. And then in the latter part, from the 26th and to the 31st, we see that there's a high probability of icing, and then we also see that there's a low production, probably because there in fact was icing and production was severely reduced. And then our clients will be able to say, okay, in this period of time, there seems to be a high likelihood that there is icing. So when I set my position in the market, I am a bit more conservative. Yes. I have another example of rare events that we predict for our clients and which are both rare, but also they cost our clients a lot of money because they have an incorrect position in their market. So in the German Bight, or actually in the big part of Germany, and typically the offshore parks in the German Bight are very much what can happen is that there's a lot of production, there's a lot of wind, but the transmission cables that transmit this power cannot transmit all the power that's needed because of limitations, physical limitations in the cables. And that means that the transmission system operator needs to shut down, or they need to limit the production from some of these parks. And that means that if we look at the lower in the plots, we see that the actual production at the black, we have time on the x-axis, we have normalized power on the y-axis. We see that the actual production is black, and we see our forecast is blue, and then we have an area, a red area, where we have marked in this situation there's a high risk of power regulation. And if we had not done anything, we would have sent the full forecast, which is the light red purple one, which shows that there's full production in this period. But in fact, there's a limitation of power, which we can see in the black line. It's flat, it does not follow the wind speed pattern. There's a interference and a maximum limit cap here. And then what we can do is we can say, okay, in these few events that we have, we can gather these, and we do not need to train a full prediction model that takes all weather parameters into account and then gives us a poor performance. Instead, we can introduce some prior knowledge, some human knowledge, saying we know that it will be flat here, we know that we might not need to, we are limiting the number of input features, so we don't need to train as complex a model for these situations, which is often often the issue with these minority classes, that we have a poor performance because we're trying to build a sophisticated model, and what our suggestion here is to use some prior knowledge and make a much simpler model in this case. This is what I had to say. I hope you have seen that there are things to consider when building a prediction model, and I hope that you see that there are also for rare events, there's a possibility of doing things slightly different than the standard approach of upsampling. Yes, I'm looking forward to questions. I think my 30 minutes has gone now.
Yeah, so I think I'm on the call now. Yeah, so
okay, yes, okay, good. Yeah.
Thank you very much. It was very interesting and also a bit complicated for a plain developer like me. But okay. It's good. And I think I can see at least there are questions coming up, but I think we'll keep them until we have Nicola. So from your frost prediction to his water prediction. So Nicola, will you try to take it from here?
Yes, and you can see my screen now.
Yeah, we can see it.
Okay, that's good. I will talk about the water prediction and with a special focus on flood and drought forecasting. And the reason why I decided to focus on flood and drought, it is because they are really extreme weather events that affect millions of people around the world, cause damages every year of billions of US dollars, and I think there is really more and more attention in the try to handling these extreme events with using forecasting system and using early warning systems. And I'll show a few examples of those. But just to start a little bit describing, okay, what is a flood and drought forecasting? How does it work? And I think in a traditional way, so how normally a flood and drought early warning system is built. There is, first of all, we have a number of data that are collected. They are typically data on the conditions in the river, can be discharge, can be water level, and conditions and weather forecasting. When I talk about real-time data on the conditions in the river, they are both usually data that are measured at the river with in situ measurements, but also satellite data. All this information that are available from the site and on the weather forecasting, they are then combined. They're feeding a what is called a hydrologic model or a basin river model. The model is maybe a little bit different from what Eben was just talking about. It's a bit different approach, because here really what is driving the way we use the data is physics. So all our knowledge on the way the water cycle works, how water is flowing in the river, all these informations are used to then combine the data that are available. And the outcome is then we can describe in real time, but also forecast how water is going to be distributed at the site, how it's going to be distributed in the river, and also we're going to be able to say some information about how the flood and the drought are developing in time and space, which area are going to be affected, how much are they going to be affected, and these information can then be used by authorities to then drive the response. And I think a very good example of this approach has been recently, and I was very happy to see that is a flood and drought is a flood early warning system that we developed in Bangladesh a few decades ago, 10-15 years ago, and actually this early warning system has been used recently in July during a major flooding in Bangladesh by Red Cross and other organizations to then drive the humanitarian activities. So that's an example of why is it important to have to be able to forecast flooding and also drought. To say a few more words about the data that are needed in a classic flood and drought system. I mean, we you first of all need to have the model in place, so have information about, for example, how the type of soils that you have, the type of the digital elevation model. You need to have some information about the river, but really to make it operation, to be able to forecast what is going to happen in the next hours and days, you first of all need to have a dense network of in situ stations that can measure weather conditions and that can measure conditions in the river, so discharge and water level. And the example I brought here about this let's say traditional flood early warning system is from Thailand, and in this case is a system that is still under development, and in this case they have, for example, about 1,000 stations throughout the country. So is really a massive effort in collecting this real-time data. On top of this, then we also use satellite images, and we use weather radar. So these are the data type that are really at the core of the system, and these informations are then used in a hydrologic model. When I talk about a hydrologic model, and I'll do that a lot, what I talk about is a numerical model, is a physics-based model that can describe the processes that affects the water cycle. So how water is, for example, once precipitates to the ground, how is it distributing in the ground? Water that is infiltrating down to groundwater, how water is flowing in a river, is going to a lake, it evaporates. So all these processes are described in a hydrologic model. But it's even more than this, because actually we can deploy different type of model depending on the processes that are relevant at a specific system. So for example, if we start including reservoirs, or if we want to be able to simulate exactly how the flood is moving, not just the processes in the river, then there is a different type of numerical models can be used here. And I've brought some examples on the right. You can see, here are, for example, 5 different, numerical or physics-based models that can be deployed to describe such a system, catchment area where flood and drought events might happen. And this, I think, this really indicates a little bit the complexity of such a flood and drought early warning system in a classical way. I have mentioned before this example from Thailand. Thailand in 2011, and actually all the region around, experienced a huge flooding event in 2011, and it affected many people. There were more than 800 people died during this extreme event, and for this reason, that was the moment where Thailand realized, or the Thai government realized, they needed to have a flood early warning system in place that could help them guide, prevent such an event to happen, or guide the different activities while the event is happening. But what I want to emphasize here is that such a system, in the in the way it is implemented in a classical way, like it is done in Thailand, where you have a lot of in situ measurements, you have a lot of different processes that are important, because you need to regulate reservoirs, you need to regulate water in cities, you need to regulate how water is flowing in the river. Such a system is extremely complex, and I think the sketch on the right side that you see here, I think it well describes that, in the sense that you can see Thailand is divided in different areas with different colors, and in each areas then they used a combination of different models that use the data that are available to then forecast flooding. You maybe cannot read all the different models that are used, but you can see different boxes, and each box is a different numerical model that is put together to describe what is happening at the site in order to predict flooding. So it's really a huge effort, and you can see also there are some gray areas, and those are areas that are not currently covered by the system. And it's a system that Thailand has started building in 2011, or a few years after, and is still working on. So it's really a huge effort. And what I would like to emphasize about this, classic flood and drought early warning system is that is really is the best system, or is the most is the best solution in case you are you need to really describe the processes that affect water. You need to be able to forecast flooding and drought, and you need to really be able to handle what is happening in different areas. The drawdowns of such or the problems of such a system is that it's costly to develop, takes a lot of time, and it takes a dense data network to do it. So you need to have a lot of in situ data. And then the other problem is that you cannot upscale to an area nearby. You are limited to the areas where you have the data available from the site. And that is why we started. There's been more and more interest moving toward, well, can we in the same way where we forecast weather on a global scale, can we forecast also water level discharge, so water processes in a river on a global scale, on a global scale, and so we'll and the answer here is yes, we can do it. We have been working in the past few years on such a system, what we have created is a global hydrologic model. So it's again a model that is using in all our knowledge on physics. So it's a physics-based model, but it's a model that covers the whole world and describes rainfall runoff processes. So how water flows in the different distributes in a different compartment once it falls on the ground, and can also simulate how water is flowing in the river. Right now, the system is almost global and has a resolution of 0.1 degree, and is running operational. So is currently running, and it can predict discharge in rivers and soil moisture in for the next few hours, for the next days, up to 10 days, and it can also have a longer term prediction, so like seasonal forecasting. And there's also 20 years historical data set. So what we base our let's say the building of our model is about a 20 years historical data set. This is a very different system in a way, just from the one that I've shown before. So the traditional flood and drought forecasting system is very different, because what we do here is that we don't rely on local data. We use global data sets, and I'll show you in a moment which type of data sets we use. But we use global data sets describing it can be precipitation, can be the type of soil, and we try to, taking the data sets that are available, we try to build on top of that using our knowledge on how water flows, on river processes, and we combine these two to then create what we could call a global data set for parameters that are relevant from a hydrological point of view. So parameters that are relevant, like water level, discharge, that are then relevant for under flood and drought situations. And as I said, is done in a forecasting mode. When I talk about global data sets, I brought here a few examples. So what are the data that we then use to build these models on? Is, for example, data information on land use, on type of soil, on the depth to bedrock, on the digital elevation model. So all these data that are now available on a global scale, then we use those to feed our hydrologic model. We also use, of course, climate model or climate forecasting, to then be able to forecast the future to forecast the future conditions. As you can see, also how is the model a bit more precisely built? We have divided the world, so we have the global data sets in the background, and then we have divided the world in 251 tiles, 432 tiles, and 251 are on the ground, and each tile has a 10 by 10 degree resolution, which is around 11 times 11 kilometer. Depending on where we are in the world. And for each of these tiles, there are 10,000 models that are running, taking this information from the global data sets and then converting them into parameters that are interesting from a water perspective. The only exception is Denmark. Here we have a resolution that is much finer. Is 1 time 1 kilometer, and the reason why we have this finer resolution is to take advantage of the these national data sets that are available in Denmark, that are at much finer scale compared to the one we can access on a global scale. So it's really to take advantage of the amazing data availability that there is in Denmark. It is also because Denmark was the first country we tried this downscaling, if we can call it, process. So try to take advantage of more local data rather than only the global data sets. So how do we go from these tiles to be able to say something about what happens in a river? Then what we do is that we have gridded information about several parameters. We also have information on the weather forecasting. So we then convert this into a catchment model. So we are able to say, okay, what is happening in the different catchment, in different river catchments, and then from there we can then calculate what happens at the different rivers, and so how water is flowing in the river. And what you see here is an example from Europe, from a catchment in France, and you can see there are a lot of the picture is a bit busy, but there are a lot of like blue dots, and there is a blue line, and those are rivers, and all the blue dots are actually points where we calculate the water flowing in the river. So we calculate the discharge, and this is possible from these global data sets I've shown before. What is exactly the outcome that we get? Well, we can say there are a number of parameters we can forecast, like for example soil moisture. But if we look on a river perspective, I think the major parameter that we get out is the discharge. And then from the discharge in the river, so how much water is flowing in the river, then we can use that to say something, for example, about flooding condition. And as I mentioned before, it's possible to forecast up to the next 10 days. It's also possible to forecast, make a seasonal forecast up to a few months. Even though from a flood perspective or water level perspective, the short-term forecast is the most relevant one. I also included in this slide a figure of Denmark. You can see it's very hard to see anything. You see a little bit of blue colors in the background, and that is because what this figure is showing is all the dots where river in Denmark are simulated, and there are just many thousand of those. As I mentioned before, is 1 × 1 kilometer resolution. So it's really a very densely network of points where we are able, thanks to the data set available in Denmark, to simulate conditions in the river. All the red dots, those are the one where we have data on discharge. So those are where we have historical observations, and those are the ones that then we can use to calibrate our model. I have mentioned it's also possible to forecast the it's going too fast. It's possible to forecast the a parameter like soil moisture. So how much water is in the root zone, how much water is stored in the soil. And this is a very important parameter when we're dealing with drought. The picture is that you can see here, there is a color from green to red. And what this picture describes is a forecast of the soil water content, where green is close to saturation and then red is close to wilting point. So what we can do here is really to be able to forecast, okay, how much water is going to be available in the root zone in different areas of the world. And this is when we're dealing with drought, and it's the seasonal forecast that is really the key element here. So what is really important, be able to say what can happen in the next few months. And these information are actually made available through the Flood and Drought Portal developed by the UNCCD, which is the United Nations Center for Combat Desertification. They provide basic tools for different countries that don't have a drought early warning system developed, because maybe they don't have the capabilities to do that. But what the UNCCD does, they provide some basic tools, and this is one of them. Together with, for example, weather forecasting and many others. So just to wrap a little bit around this global flood and drought forecasting based on global data sets, what I think is really the key thing, what is really the big advantage, is that it's not limited to areas where we have data. It applies to global data sets, which means that it has a nearly global coverage and is already operational. So it's already running, is already available. It's not something that is going to be ready in 5 years. There are, of course, some limitations, and the first one is there are a few physical processes that are included, or only natural river systems that are included. So effect of reservoirs is not accounted for, can be included, but it's not as it is right now. The other limitation is, of course, resolution, which is depending on the needs, on the local needs, can be a problem. And I think also another let's say, problem or limitation is the fact that there are no in situ measurements. So we only based everything on global data sets by choice, but this is actually something we are working on together with Blue Fragments, is actually to be able to, account also for in situ measurements together with global data sets for some specific areas. I'll now jump to a very different. So I've talked about a classic flood and drought system and a global system. I'll now talk about another way of forecasting flood and drought, which is again very different and actually is a little bit more in line to what Eben was talking about before, because what we do here is that we focus on a data-driven hydrological forecasting system, which means we don't take into account all the knowledge that we have on physics processes. So we don't use physics-based models, but what we use, we just use the data. And the reason why this is important, it is because in some cases where you have a good data set, and this the example I actually have here is from Denmark. You can actually you can take advantage of the data that you have available and let those data drive your forecasting. And some of the advantages, of course, that has a short computational time compared to a traditional model, can run very fast, and this is well suitable for a real-time forecasting system. The other, I think, interesting part is that some of the workflows can be automatized. So the system can be, in a way, upscaled or moved to other areas without having to start from scratch with a new model that can take, or numerical models that can take a long time to build. The example I have here is actually a collaboration with the Danish EPA, Miljøstyrelsen, and the idea here was, can we take advantage of water level measurements of the many water level stations that are available in Denmark, and can we do that to be able to say something about how flooding is looking right now. So if we have real-time data, how can we say something about how flood are looking right now, how they are developing? But can we also combine this information on the current water level, historical water level, combine it with precipitation or weather forecast using machine learning algorithm to then be able to say something about how flood are going to develop? So looking to the forecast using a machine learning approach. I'll not say too much about the method, also because I think Eben has touched on some of the points here. But I mean, the idea is really to you have the data that needs to be prepared, and then you have this data then used to train a machine learning algorithm that then is used to predict, in this case, is water level or water discharge in the river. I'll just show one very concrete example, just to give you a little sense of how different we are from, for example, the global approach. Here, what we use is, how our focus is, can we predict the water level in a point in the stream, and it's a point where we, of course, need to have a long time series where with observation on water level, and the other data that we need are weather data, so historical data collected at the weather station. So these are actually the data set that are used in this case. They're very different. They're all in situ measurements, measure at a specific point. We don't rely on the global data sets as we did in the other case. This of course, and just to show a little bit, okay, so what can we actually predict? I've brought here a little example where you can see in the background there is a red and a blue line. The red line is the observed water level over a 2-year period in the river, and the blue one is the what I call forecast. Is maybe simulated is better, but what we do here is that every day we make a new forecast on the water level, and we just assemble them, we put them together, so we can create a continuous line that then can be compared with the observed water level. And of course, the forecast is, if you look up on the upper right corner, there is this figure showing the R-square and the mean average error. And I think what is, of course, important to account here when we talk about forecasting is that, I mean, the forecasting horizon is really important. So how long in the future are we trying to forecast is of course a very important aspect, because the forecast is going to deteriorate over time. So we can predict quite well what happens in the next few hours. The longer the time, of course, the more challenged we are, and the higher the error that we get. But I think all in all, it was in this example, I think we have quite a good forecasting. For example, we have about 30 days over a 2-year period that are not within the target, which was 10 to 15 centimeters error. And this, of course, very important, because when we are dealing with flooding, when we are dealing with early warning, we need to be able to be within the target that is we need to be very close to what is actually the actual water level in the river. There are though some I think some interesting aspects, and one of them, and actually this is again something that Eben was mentioning before about these rare events, or events that are in this case that are not covered in the training period. So what I have shown here is this 2 years period, which is the test and validation period for this machine learning approach. We had before that about I think it was about a 10 years period for training, and during this 10 years period, the algorithm had not experienced a dry summer, which was as dry as the one that we have experienced in 2018, and this is what explains the difference that you see in the red and blue curve during the summer 2018. So it was a very dry summer, and which meant that the algorithm, or the model in this case, could not deal with these conditions. Again, it was not a big problem in this case. We're interested in high water levels. We're interested in flooding condition, which is not, of course, what happens in during the base flow. But it is something to keep in mind, and I think in this sense it was quite interesting what Eben was describing before about rare events. Just to show a little bit, I talk a lot about water level in this approach. Water level is then used to say something about flooding, and what I've brought here is the blue maps are flood maps that were made for conditions for two historical flooding event, and then we compare those with how we do make sure that they are correct. We use, of course, pictures that are taken on the site, but we also use the satellite images and drone images to then make sure that the flood maps that we make are representing reality, and then based on that also to adjust our flood forecasting method. So just to summarize a little bit about this machine learning approach compared to the physics-based models that I've shown before for flood and drought forecasting, I think the real strength here is that is as a short computational time compared to the model I've shown before, and this makes it very suitable for real-time forecasting, and the fact that the workflows to implement a new site can be automatized at the level that makes it quite easy or relatively easy compared to the traditional physics-based model to implement. There are, of course, some limitation, and I think a major one is that we are limited to forecast points, areas where we do have measurements, and this can be a big challenge, because we don't have, if we look, for example, at water level time series, they're not available along the whole river. They're available at single stations, which are normally not many in a single river. The other thing is, of course, and this applies more or less to all systems, is that the forecast quality is highly dependent on the climate data forecast quality. But I think what is different mainly different compared to the physics-based model is that the machine learning approach relies on conditions, on situations that were met during the trading period. So all what is future scenarios or scenarios that are that happens very rarely, they cannot be described. And I think this is a big, in a way, a big limitation compared to physical-based model, because they're actually the physics-based frameworks actually help, forecast, or at least be able to say something about what could happen under conditions that are very different to the one that were used during trading. So I'll just conclude saying that, and I hope I want to make this message very clear. I presented the three solutions as somehow something standing alone. So you have a traditional early warning system that is very complex, heavy relying on models. It takes a long time to build, heavy relying on in situ data, and then we have to a bit, we can call them more newer solutions, where we have a data-driven hydrological forecasting, which is based on machine learning, is based on time series collected at the site, and a global hydrological forecasting, which is based on global data sets. But actually, these three solutions are, in a way, what we are doing more and more is actually to combine the three in let's say in hybrid solutions, where they are all three, based on the needs at the site, based on the data available, then they are combined in a way that can really suit the what is needed. And I think a good example is, for example, the work that we're doing with blue fragments, where we use as a base this global hydrologic forecasting. We actually use the Danish hydrological forecasting, and then we combine that with in situ measurements, using machine learning, using data simulation approaches, to then be able to refine and target local areas with this approach. And other work that is, for example, done, and this is also in Thailand. We use for example, a combination of the traditional early warning system, where it has already been established, but we actually combine it with the global hydrological forecasting to be able also to guide, not with the same level of accuracy, but at least be able to say something in other areas which are not yet covered by their forecasting system.
Nicola, is that the rounding up you're doing now?
Yes, it is. I'm done.
Perfect. Super. So let's, I think it's time now for some questions. So I think I'll let you, and then take the questions first. There's some on the chat, and there's some on the
Yeah, so we have
on the mail afterwards.
Yeah. So there's one on the chat. I think it's primarily for you, Eben, saying, is icing the only effect on power production? You mentioned to consider multiple parameters in the bias model. What other parameters have you considered?
I hear there's two questions, but I might be. So one thing is icing the only thing that affects power? No, definitely not. But it's something that's happens so rarely, so it's not typically part of the typical power forecasting. What other? I mean, that's a lot of stuff that affects the power production. The age of the turbines, and the number of turbines, and the wind direction, and the wind speeds, and the temperature, and there's a lot of things that. But those things are typically already in the prediction model. And then there's a question. Then there was what else? What other parameters have we considered in this? And I hear it as what other parameters have we considered specifically in this base network for the icing? And This is it's a work in progress. So we are still working on expanding it. But currently we are, if you want to know very specifically, we are using the relative humidity, and we're using the temperatures at the surface and the temperature at the hub height, and we're using hour of the day there's a time aspect here. We're using visibility, and we're using the season of the year. Other parameters that we are considering expanding with is the mean of the temperature over the last couple of hours, maybe. We see that there's, or it makes sense that there's like a build-up of icing. So it's not at a specific temperature, but it's as when the temperature has been low for a while, maybe. We also considered, but didn't see an effect, but we also considered using the solar radiation flux. I mean, how much, I mean, the radiation of the sun, as you could say, maybe that is something that maybe heats up the ice. So there's a lot of considerations in what parameters to use.
Perfect.
And a challenge is actually also that some turbines has heating in the blades. So even though the physical, the meteorological conditions are there for icing, we don't see the effect of icing because the blades are heated. And that sort of makes the model building a bit difficult.
Yeah.
Yes.
Perfect. Thanks. Yeah. So now it was very interesting for me to listen to both of you. You mentioned some of the troubles that you're in with the data sets and so on. And you can do a lot of awful things. So what is next to come? What is the next thing you can predict, or is it just that you are getting better and better for what you already predict, or do you think you can predict new things in the future? And if so, what?
Are you asking me or Nicola?
Both of you, so feel free.
Yeah. Okay, yeah, we are now, I mean, we are focusing more and more on these rare events because we are, you would say, our basic power forecast, when you say, when everything is as it usually is, you could say. So our basic forecast is relatively good. What we are trying to look at now are rare events, such as icing. When there's icing, there's something happens that affects the power. When there's this downregulation of power that we see often in Germany, there's a change in the power output. That can be, we have some other issues with, there's some timing in the numerical weather prediction models that makes, if there's a fast ramp up or ramp down of power, let's say we have a low wind speed, and then all of a sudden there's a huge increase in the wind speed. Then we go from a very low power situation to a very high power, and so we'll see that there's a high slope in the power forecast or in the power production, and timing that is a difficult challenge, and so we are looking into these events where we are where the power production forecast is challenging.
Yeah. Okay.
Yeah, and I think from our side, the focus is very much more and more on being able to, given the data that are available, given the resources that are available, being able to forecast as good as we can, as much as we can in different areas, and with the flexibility of do it on a more with a less resolution, on a more maybe also less accuracy in some cases, but being still able to say something for areas where there are not resources to be more specific or go more in details, do more work, and then at the same time also be able to be detailed and have very good early warning system, or very accurate early warning system in areas where there's really the need for that. So I think it's that flexibility which was in a way missing before, because before we just had the the heavy modeling data work that we used to do. I mean, that ability to have this more flexibility. I think that's really the work that we're trying to do more and more.
Yeah, and when we are at that, then there's a question for you, Nicola. Do you think it's possible to predict a bit longer term groundwater levels from your model with machine learning, connecting model results with groundwater level progress with machine learning?
Yeah, this is actually a very, very interesting question. The machine learning approach I've shown has actually not been tested on groundwater. Has only been used on, or at least we have only mainly used in rivers, because as I mentioned, we had a lot of focus on flooding with together with the Danish EPA. But I think actually this point on groundwater is very interesting, and I definitely think it would be interesting to look into that. And I think it would actually be possible, but I mean, has to be tested. We haven't tried that, so.
Okay, thank you very much. There are no further questions in the chat, and it was a pleasure listening to you. Hope other than me enjoyed it. And as you can see on the slide, the next event is visualization of data on the 18th of November. So I hope we'll see all of you again then. And then for now, Iben and Nicola, thank you very much for your talks. It was a pleasure listening to it.
Thank
You're
you.
welcome. Thank you.